Hello, this is Mr. Craig, and this is quiz number 2 for period number 2. Let's go ahead and get right into it. Questions 1 through 3 refer to the following elements or compounds. Number 1 is formed from an incomplete combustion of hydrocarbons. Remember when we talk about hydrocarbons, it's some carbon, hydrogen compound, and it always reacts with oxygen to form carbon dioxide and water, and that's from the complete combustion of a hydrocarbon. Well, oftentimes something doesn't occur correctly, or the carbon dioxide will only get one of the oxygens for some strange reason, because it is quite easy to make carbon monoxide as well as carbon dioxide. That's often why if you have a gas furnace in your house, you probably should have a carbon monoxide detector, especially if you have an older furnace. So the best answer for this one would be letter B, as in boy. And how would you know that? That's just something you have to know. There's no way to predict that carbon monoxide is going to be formed in that after being told over and over and over again. And again, our reactions, especially in class, we're always dealing with a perfect situation. All the conditions are ideal where we can always make our products that we expect to take place. But in the grand scheme of things, sometimes one oxygen doesn't jump on with the other oxygen to make carbon dioxide. So yeah. Number 2 is soluble in carbon tetrachloride, or CCl4. Often when you see a question like this, if you're wondering about whether it's soluble or not, you probably should draw the Lewis structure, because by drawing the Lewis structure, you'll see a lot of things about this compound. Hopefully I won't scoot up too far. Excuse me. But when you draw this thing out, you see that the carbon tetrachloride actually has all its carbons bonded. Therefore, what kind of compound do we have here? And what I mean by what kind, is it a polar, non-polar? Because when we talk about solubility, we're always talking about like dissolves like. And what does that mean? Well, if you want something to dissolve in water, water is a polar compound. You need something that is also polar. So the compound itself must be a polar compound. Now, this is a non-polar compound, but this also has polar covalent bonding within it. Now, I don't want you to mistake the two. A polar compound is totally different than a polar covalent bond. Polar covalent bonds simply mean that the two atoms, in this case the carbon and the chlorine, are not sharing these electrons equally. Whoever has the higher, greater electronegative value will have those electrons that are being shared a little bit closer to them. And excuse me, I think chlorine is 3.0, and I can't recall. But if chlorine has a higher electronegative value, then it has a partial negative charge, where the carbon would have a partial positive charge. So that's getting beyond what this question's asking. But when we talk about polar and non-polar compounds, don't mistake that for a type of bond. And again, I wasn't the one that named all these things. And especially for general chem students and like yourself, those same names can often be confusing. So just be careful with that. So C. Oh, I'm sorry, I didn't even complete the question here. The reason why it's C is because iodine is the only compound, when you draw this out, that forms a nonpolar structure. Everybody else, like the HO2, that's polar. Carbon monoxide, we know that's polar. Calcium iodide, that's an ionic compound. All ionic compounds are polar. And SO2 might be the one tricky one, but it too is polar. So we're looking for a nonpolar compound. Probably should have showed you the answers first, or the options first. Alright, number 3. Exhibits the bonds with the most ionic character. When we talk about ionic bonds, it can be between ions, or it can be between compounds. because it doesn't say if it's inter or intramolecular. The nice thing is the ionic bonds are always with ionic compounds. There's only one ionic compound on here. Now you might say to yourself, excuse me, that the hydrogen and oxygen could be considered an ionic compound, since hydrogen is on the periodic table way over here on the left and the oxygen's way over here. Hydrogen's one of those elements that can swing either way. It can be a nonmetal or a metal. So whenever it's with carbon, oxygen, we're going to go ahead and say that it's acting like a nonmetal. So really the only choice is D for this option. Alright, number 4. How many unpaired electrons are in a gaseous iron atom in its ground state? Alright, so how many unpaired electrons? Well, probably the best way to answer this is by doing the electron configuration. So let's do the shorthand. We know that all the electrons in the rows above are filled. We know that. You have to know that. Alright, so since iron's in the 4th row and the last noble gas before iron is argon, let's go ahead and draw the electron configuration here. You go away. So we've got argon, and again we're drawing this for neutral. Should be ground state. Doesn't say it's neutral. Yeah, atom. There we go. So, so 4s, it has those in there right now, and then 3d, 1, 2, 3, 4, 5. Let's see how many over iron actually is. Where is my cursor? Fine. So we have 1, 2, 3, 4, 5, 6. So iron is 6 over, so we're going to go 1, 2, 3, 4, 5, and 6. Now, do special stabilities apply for this situation? In other words, can I take electrons out of the 4s here and move them over to have in this case, an empty s and looks like trying to get a full 3d or a half-filled d? The answer is no. So the electron configuration is going to remain as we have written it right here. And again, we always want to drop one electron in each orbital within that suborbital region, so to speak. So it wants to know how many unpaired electrons are in the gaseous iron atom. Well, 1, 2. So we have 1, 2, 3, 4. Should be B. Okay. So again, draw out the structure. You have 1.2 minutes for each of these. Don't make a silly mistake on something like this. Oh, and I didn't even mention the gaseous. All right, number 5. In which species is a central atom surrounded by exactly 8 valence electrons? Well, if you're smart about this kind of question, do realize this. When looking on the periodic table, carbon, nitrogen, oxygen, and fluorine can only have 8. And they have to have at least 8. They can only have 8. However, the nonmetals below them, phosphorus, sulfur, chlorine, as central atoms, and down here below, they have something that these elements here do not have, and that's these d orbitals. Okay, so when looking at a question like this, realize, hey, I've got bromine, that's below that first row. I've got iodine, that's below the first row. I've got sulfur, that's below the first row, and there's a 6 there. Phosphorus below the first row. Your only option is E. Okay, if you want to draw it out, that's fine, but remember, everybody has to have at least 8, but those 4, carbon, nitrogen, oxygen, and fluorine, can only have 8. They cannot have any more because they're in the second energy level. There are no 2d orbitals. The d's begin at 3. Okay. Number 6. Which molecule contains 3 sigma and 2 pi bonds? Well, got to draw it out. So we're looking for 3 sigma and 2 pi. Now, so the 3 sigma, now do remember what sigma represents. A sigma represents a single bond. We could have a sigma pi to represent a double bond, and we can have a sigma pi pi to represent a triple bond. Now, let's be smart about this. Since there can only be 3 sigma bonds, there's got to be three total sigma bonds. Okay? So that means when we look at something like this, we know that we all have carbons here. So if we put a carbon and a carbon there, okay, we're almost done. So we have 2 of the carbons. Okay, boom, boom, boom. That one's got to go. There's no way. That one's got to go. So now we're down to these situations here. Now, if I had 6 hydrogens, think about this. Without even the carbon-carbon bonds, how many sigma bonds would we have? Well, we'd have way over 3. If we looked at this one, the 4, there's no way we could have 3 sigma bonds when there's 4 hydrogens. So that one's out. So now if we look at this one, that has to be our answer. And if we correctly draw this out, okay, we have the hydrogens have to be single bonded. And then carbon, each carbon wants to have 4 bonds, so that means that carbon's going to have a triple bond. So there, the 2 singles, those are your 2 sigma. The 1 triple has a sigma and 2 pi bonds. So A has to be the answer in this case. So again, think about the types of information that's presented to you when you're asked a question like this, because that'll eliminate you having to write out all the Lewis dot structures if you know what the 3 sigmas actually represent. Alright. Number 7. This molecule forms dsp3 hybrid orbitals. Make sure that you know what dsp3 represents. Do know this, that if we had sp, that's for our linear shape. If we had sp2, that's for our trigonal planar. Now again, below the trigonal planar, I don't know if I have enough room here, and then we could have bent immediately under that. And then for sp3, that's your tetrahedral shape, and then trigonal pyramidal, okay, and then also bent again. And then dsp3 is your trigonal bipyramidal, and then below that you have seesaw, and below that you have T-shaped planar, and then below that you have linear. And then in the last one, hopefully I've got room, if not I can write it down here. In the last one you have D2 sp3, which is your octahedral shape. Now if I remove 1 electron from there, I make a square-based pyramid, so square pyramidal, and then the last one for that is your square planar. Okay, so make sure that you know what these hybrid orbitals represent. You have to know these. I guarantee you'll be asked hybridization or shapes or Lewis structures on question 5 or 6. It will be there. I promise you. It's been that way for the last 6 years. It's going to be that way this year. Alright, so this molecule has dsp3 hybrid orbitals, so we're looking for a trigonal bipyramidal shape. We're looking for one of these guys right here. Okay. So if I look at water, no. If I look at methane, no. Why? Because this is a bent shape that is within a tetrahedral shape. This should be a no-brainer. You shouldn't even consider looking at that. Alright, coming over here, looking at the SF6. Since I have 6 as my external atoms, this is an octahedral shape. That one's out. Sulfur trioxide, it's either a trigonal planar shape, which it is, or a tetrahedral. So that one's out. So it's got to be IF3. Now, let's just double check. Alright, so we know that iodine has 7 electrons, and fluorine brings 7 times 3, so that's a total of 28 electrons. Iodine's in the middle. We have 3 fluorines around it. So that's a total of 24 electrons, and then whatever's left, put on a central atom. Okay, so we have our potential as 5, so that means that we have dsp3 hybrid orbitals, or a trigonal pyramidal shape. That actually forms a T-shaped planar, and if you look at it, we have our T here, and that T lies on a plane. All right, number 8. Which is the correct comparison for chlorine atom that has no charge? That means no charge. And a chlorine -1 ion. All right, number 1. The radius of the chlorine atom is greater than the radius of the chlorine -1. Well, hopefully you remember that being bigger can be a negative thing. So that's the case here. So the radius of the chlorine -1 is greater, not this one. So that one's out. The mass of the chlorine atom is about 1 AMU greater than the mass of the chlorine -1 ion. All right, what's the difference between chlorine neutral and chlorine -1? It has 1 electron. The mass of an electron is so small that we don't even consider it when we're doing molar masses. It has a mass, but it is so small. An AMU is either the mass of a proton or a neutron. So adding 1 electron will not increase it by 1 AMU. So it has to be 3. Alright, so the chlorine neutral atom contains fewer electrons than the chlorine -1. That is absolutely true. Because if you look at chlorine with the -1, it has 1 more electron than it originally started with. So where's 3 on B? Alright. When the concentration of a particular reactant is tripled and the initial rate of the reaction increases by a factor of 9, what is the order of the reaction with respect to the reactant? Alright. So what's happened is a particular concentration is tripled. So we go from 1x to 3x. And let's say that we have 1 molar, and then the concentration is tripled to 3 molar. Is that right? Tripled, and the rate, oh, I'm sorry, the rate goes up 9. My bad. Sorry, guys. So it goes up 9. Alright, so what must the rate of the reactant be? Well, don't forget that if we say that we're looking at some substance, whatever that is, if it's a 0 order reactant, if we have a 0, okay, if I triple the concentration, what happens to the rate of the reaction? Nothing. It stays the same. It does not care what the concentration is. The rate remains the same. Okay? Let's go through the first order. If it's a first order reactant and I triple the concentration, what happens to the rate of the reaction? It's 3 times faster. Okay? So if I look at a second order reactant, if I triple it, or if I say 3 squared, it's an exponent, it'll be 9 times faster. So my order of the reactant must be 2. Okay? Now, you can be given situations where, and it's highly unlikely because you won't have a calculator in front of you, but do realize that you could, and I'm just giving you a horrible situation here. Come on, erase, please. Okay. Let's say that you are given a reaction where it has A is second order, B is first order, and C is second order. Let's say that, just to be nasty here. Okay. So what we know the order of each reactant: second order, first order, and second order. What's the overall order of the reaction? Well, it would be 5. So it would have an order of 5. Okay. So if I if I increase the concentration by 2, okay, I double the concentration for everybody here, what will my new rate be if I start off with 1 molar concentrations for everybody here initially, and my rate is, we'll say, 1x, okay? And then I change the concentration for all these to 2, okay? So I double the concentration for all these. How much faster will the reaction go? Well, whatever that is. So 2 times 2 times 2 times 2. And I don't have a calculator. So 4, 16, oh God, I can't do this in my head. So whatever 2 to the 5th power is, that's how much faster this reaction will go. No, you will not be asked to do that on a piece of paper, okay? But this problem right here, absolutely, you should be able to do that, no problem. Okay. Number 10. Which of the following molecules has a loose structure containing 1 double bond? Alright, now again, Lewis structures. We should be able to do some of these in our head if you do these often enough. Let's start the back here. Hopefully you have carbon dioxide memorized. Carbon dioxide is a linear shape. Okay, so no, it has 2 double bonds. Nitrogen. Nitrogen's a group 5 element. It wants to have a triple bond. Okay. OF2. What does fluorine want? And again, recall when we go back to our looking at formal charges, everything here, over here in group 7A, wants to have a single bond as an external atom. Everything here in group 6A wants to have a double bond as an external atom. Everything over here as a non-metal wants to have a triple bond as an external atom. So we have to realize that. So one thing to keep in mind too is if there's only 2 atoms, they're both external atoms. Okay, so going back, sorry. So we have fluorine with single bonds, so it doesn't even have any double bonds. Water, well, hopefully again, we know that hydrogen can only be single bonded. So it has to be this. And it is, because when we look at the shape of the compound, okay, we have carbon with a double bond, because again, carbon wants to have 4 bonds. It looks like that. So you have 1 double bond, so A. Number 11. A sample gas at 273 has a pressure P1 and a volume of V1. When the pressure is changed to P2, what is the volume of V2? Now, again, you don't have to memorize equations, but this is Boyle's equation. Okay, and actually, to back up the wagon a little bit further here, if we have this situation, PV equals nRT, we have a before and after situation, which means that we get to use this twice. Okay, so when we do this, we know we have an initial pressure, an initial volume, and then a final pressure and a final volume. The neat thing about this equation is we don't have to rearrange anybody. So when we write all this out, why won't my pen do it the first time? This is actually what the equation is saying. That here's our equation. Okay, we know that these are not going to change. So now our equation is this. Alright, so now that we have this equation and it wants to know what is the volume of V2, so what that means is to get V2 all by itself, we have to move P2 down. So whichever one that is, looks like this one, E. Okay. Again, why do you think I preach all year long about rearranging variables before you start plugging any numbers in? Because you will see questions like this on the AP exam. Also, the graders in the free response section want you to show the rearrangement. Don't just plug in numbers and spit out a value. That's what you do in math class. That's not what you do in the real world. Alright, number 12. Manganese forms a number of oxides. A particular oxide is 49% half mass of manganese. What is the simplest formula for this oxide? So it looks like we all have manganese and oxygen compounds. Manganese has a molar mass of around 55. Let's just say 55. Okay, so manganese is 55 and oxygen is 16 for each oxygen. So we're looking for a compound that has about half. Well, 55 to 16, no. No. Here it's getting a little bit closer, but 64 and 100, no. Getting a little better, it's 55 and 32, well, no. So now here we've got 7 oxygens, and I don't want you to do the math. We've already eliminated the 4. Okay? So try to find something that is about. So if we look at it, we've got, okay, about 110, and then oxygen 16 times 7. If you kind of round that up by, say it's 20, so it's about 140, but you get to knock off 4 of those, so knock 20. It's very, very close. So E's our best choice in quick math. Don't sit there and actually write it out on paper. You don't have time to do that. Alright, number 13. Which is a list of elements in order of increasing metallic character? Alright, so looking at the periodic table. Metals are over on the left here. Okay, so actually let's get the General Chem table up here. this bold black stair step, which you do not have on your AP periodic table, separates the metals from the nonmetals. So again, make sure you know your nonmetal triangle, which is carbon to fluorine to iodine. That's our nonmetals that we care about. Okay, so if it's touching any of those are the nonmetals that are typically going to dance for us. And then the others are just metals. Okay, so metallic characteristics go like this. As you go from left to right along the period, the metallic character decreases, gets lower. Okay, we say that it's less metallic. Everything has metallic characters at some point or another. It's just like saying, okay, even though I'm a man, I have an X and Y chromosome. Okay, I produce more testosterone than I do estrogen. Okay, that's a good thing. However, if you're a female, you better be producing more estrogen than testosterone. You are producing some testosterone. And unfortunately, when you get older in life, you don't produce as much estrogen and you start producing more testosterone, which is unfortunate. However, so we're not saying that nonmetals are metals, they just have some metallic character. And then the other trend is as you go down a column, okay, then metallic character increases. And we have to know that when we're writing chemical formulas. So if I compare sulfur and oxygen, these are two nonmetals that make sulfur dioxide, sulfur trioxide. Why do we write S first? Because it has a higher metallic character than the oxygen does. So it doesn't mean that it's a metal, it just means it has higher metallic character. Alright. So coming over here, Si, P, and S. So silicon, phosphorus, sulfur. Silicon, phosphorus. Nope, that's decreasing metallic character. Arsenic, phosphorus, and nitrogen. Arsenic, phosphorus, and nitrogen. Nope, that's decreasing. Again, you got to go down to increase. Strontium, calcium, magnesium. Strontium. Where are you? Strontium. What? Strontium, calcium, magnesium. That again is decreasing, so it gets more metallic as you go down. And then bromine, selenium, arsenic. Bromine. Yep, there we go. Finally, we got one. Boom, boom, boom. Alright, so again, these are not metals. However, they do possess an increase in metallic character. I know it's not fun. And again, periodic trends. Gotta love them. Alright, number 14. What value should be reported for the burette reading shown? Alright, so we have a burette here, and we have our meniscus, and on the actual quiz I apologize for how faint that was. And again, a burette starts at 0 and goes to 50. So we want to know how much of the titrant we've actually used. So E's out right off the bat. We are at 23. Okay, no. We do know that we've used at least 22. Okay, so now that gives us A through D here. Here's what we have to do. We have to write down every value that we know. So we know that we've used at least 22 mils. Do we know any more? Actually, let me erase that so I can actually see it. Okay. And then I know that I've used at least 1, 2, 3 more. Okay. And then I'm not real sure about whether it's between these two. Okay, so now I have to estimate. So the rule is you write down everything you know and then you make one estimate. So I'm saying it's about halfway in between there. Well, my best answer is C. Okay, here's what you would not do. You wouldn't look at that and say, we're going to round up, we're going to round down. No. You write down everything you know, and then this last value here is your estimate. Okay. Then you wouldn't even think about going any further. Like saying, yeah, I've got a really good eye, I can see that. So whenever measuring something, always write down everything you know, and then you make one estimate. Sounds repetitive, sorry. Alright, 15. For which of these is the delta H not equal to 0? So we're looking for something that does not occur naturally. Okay. Bromine. Is bromine a liquid at room temperature? Chlorine's a gas, bromine's a liquid, iodine's a solid. Good. So that is 0. Iron definitely is a solid. Iodine, we just said, was a solid as well. Again, chlorine, bromine, iodine, solid. Chlorine liquid. Wah, wah, wah. Chlorine is a gas at room temperature. Mercury is a liquid. So again, what this is asking is, look at the different states. When we're looking for a heat of formation, and if it's a 0 value, we're looking for the correct state for that situation. I think I still have colors. Yeah, I do still have colors on here. On my, or if you had me for General Chem, I gave you a periodic table that looked like this. If the color is black, that's a solid at room temperature. If it's red, it doesn't mean it's a noble gas. It simply means it's a gas. And then if it's blue, then it's a liquid at room temperature. I thought gallium was supposed to be blue. Huh. Oh well. So bromine, mercury definitely are liquids at room temperature. All right, number 16. What are the signs delta H, delta S for the reaction that is spontaneous at any temperature? Okay, so again, we're looking for delta G, and we're using this equation here, T delta S. Okay, so we want delta G to be negative, so that means we want everything over here at any temperature. We would like for all of these to be negative values. So the heat has to be a negative value. Now, that negative here, okay, is really important. The temperature here will always be positive because it's Kelvin. So if the temperature is positive and we have a negative sign here, then our delta S must be positive. In other words, the universe, delta S, deals with entropy, chaos, disorder. We want that to be taking place. So here's our situation. C. Okay. Number 17. Which salt produces the most alkaline solution at a concentration of 0.1? Alkaline means basic. I don't use that term very often, but it is nice to know what alkaline means. Doesn't mean that it's, I think it came from the term from the alkali series where you have the alkali earth and alkali metals, that when that's hooked up with OH, that it forms bases. That's the only thing I can dream up here. Alright, so which salt produces the most alkaline solution? If we have an OH on here, we're in good shape. But we don't. So let's go through it. So we have potassium nitrate. That is a conjugate of a strong base, conjugate of a strong acid, which does nothing to the pH. Magnesium chloride. Magnesium's a conjugate of nothing, unfortunately. And chlorine's a conjugate of a strong base, so nope. Because again, when we think about magnesium hydroxide, it's not soluble. That's why it's a conjugate of nothing. It's a conjugate of a precipitate, is what it is. Alright, ammonium chloride. The chlorine is a conjugate of a strong acid, which does nothing, and the ammonium is a conjugate of a base, ammonia, which is our most popular weak base. But unfortunately, since ammonia is a conjugate of a weak base, it acts like an acid. Out. Looking at sodium. Sodium's a conjugate of a strong base, and it will do nothing. But nitrite is a conjugate of a weak acid. And what do conjugates of weak acids do? They cause a solution to become basic. Okay, and then carbonic acid, no, makes it acidic. Alright, so D is our best answer. So make sure that you know your 6 strong acids and your strong bases. Real quick, what are your 6 strong acids? Well, come over back to the periodic table. We have hydrochloric acid, hydrobromic acid, hydroiodic acid. Okay, that's 3. So chlorine, bromine, iodine. And then you've got sulfuric acid, perchloric acid. I have also seen in some of these study books that chloric acid is also strong. You do what you want, but I'm sticking with perchloric. And then the last one is nitric. Okay. Alright. And then the strong bases, got to go back to the periodic table. It's all of group 1A minus the hydrogen, obviously, since it's water. So it's group 1A and then calcium on down. Okay? Alright. That's the easiest way to remember that. And the good news, on the exam, I haven't seen them use a base from over here on the free response. So bases over in group 2, I think you're safe. Know that if it does show up, that you can get twice as many hydroxides from that, because calcium hydroxide, think about it, calcium hydroxide has 2 OHs, and if it's strong, these are going to dissociate into calcium ions and 2 OHs. Okay. Alright, 18. Oh, here's the humdinger. Okay. This is a question that I would definitely circle and return back to. Okay, there's a lot of stuff going on here. And if you never got to it, I don't think I'd lose any sleep over it. Alright, here's the problem. It says we've got 50 milliliters of a 0.2 molar hydrochloric acid solution is mixed with 25 milliliters of a 0.01 molar sodium hydroxide solution. It wants to know what is the pH of the final mixture. Well, we got a lot of things going on here, yet even though we have a limiting reactant, a stoichiometry problem, we do have an acid reacting with the base. So the first thing that we need to do is make sure we have enough room to work. So we've got our hydrochloric and sodium hydroxide. What kind of reaction is this? Probably this is a good time to talk about this. This is an acid-base reaction. Actually, it's a neutralization reaction because we're going to form water and a salt. Okay. We have 50 milliliters of a 0.02 molar, and we have 25 milliliters of a 0.01 molar. Okay. So again, the bad news is you have different molarities right off the bat. However, do realize that it is a 1-to-1 ratio here using moles. So can I think logically and smart about who the limiting reactant is on this? Because, hey, we're looking for the limiting reactant so we can have the pH here. All right, so we have 50 milliliters of a 0.2, 25 mils of a 0.01. So this definitely is a limiting reactant. We have fewer volume, we have less volume, and a lower molarity. Okay. All right. So what we need to do is, so right off the bat, what should the pH be? Should it be acidic or basic? That's right, it should be acidic, so we can automatically eliminate 2 of these right off the bat. All right, so we've done well just by doing that step right there. Okay, so we've got 50 milliliters. And since we know the limiting reactant is that, let's find out how much remains. I'll do this quickly. 1,000 milliliters, 0.01, and then we'll go mole ratio, which is 1-to-1, and then we'll flip it over and go to 0.02, and then find out how many milliliters that is. Okay, so you can automatically see that there's a lot going on here. Good news, thousands cancel out. We have 25 times 0.01, which is 0.25, and then we'll divide that by 0.02, so 0.02, which means that we're going to use 12.5 milliliters. Alright, so we used 12.5 milliliters of the hydrochloric acid is what that calculation was for. We started off with 50. We used 12.5. So that means we have 37. Is that right? Yeah, 37.5 milliliters remaining. Alright, 37.5 milliliters of hydrogen ions. So what we have to do with that, hopefully I'm not showing the answer here. I need some room to work. Okay, good. So I need to find out how many actual moles that is of the hydrogen. Again, this has already taken me over 1.2 minutes. So if I know the volume and the molarity, always start with the volume at 0.02. So, shoot. draw my cute little line there. Oops. Alright. Well, what happened to you? Huh. Alright, so we have 37.5. Actually, 0.0375 times 0.02, which is 75. 75, is that right? Daggone it. I don't know why I can't do this in my head. And then, so we need to bring it over. Did I do that right? Sorry, guys. I think it's that. 3, 4, 5, 1, 2, 3. I think that's right. Okay, so that's how many moles we have. I think it's that. 0.0075 moles. And then what's my total volume of the solution is 75. 0.075 liters. Okay, so I've got 1 0 there, 2 zeros there, so that equals 0.01, I believe. And I'm doing some real quick math. And I believe that's right, because if I take the negative log of that in my head, 0.01, that equals 2. Now again, guys, do not spend 5 minutes working on this in the first hour of the exam. If you see this question, circle it. If your pen will work, circle it and come back. Okay? Here's the actual process that I used. I think I did the same thing here. There it is. Okay, so again, I found out who the limiting reactant was. I did not need to do that step. I did need to find out how much I used, though. Yeah, I did that right. Woohoo! Man, that was not fun. Alright, number 19. Oh, here we go. The reaction A plus B is first order in A. Which plot will be linear? Alright. Make sure, because you're either going to see this on the multiple choice portion or you'll see it in the free response where you get an opportunity to draw it. Make sure that we know what the slopes are for each order. Okay, so if I have my first situation where I have concentration of A versus time, and how will I get a straight line for this? Boom. Okay, what order does that represent for? We need to know this to get the straight line. This is a 0 order reactant. Okay, if I do the natural log of A, nice bracket, versus time, and I get a straight line. That's for first order. And then for second order, to get my straight line, I actually need to take the inverse of the regular concentration versus time, and that will give me a positive slope. Okay. Ooh, positive. Positive goes the other way, cowboy. Okay, positive. This way. There we go. Alright, so positive slope for second order, and the other orders are negative slope. However, be aware of what the units are here. Okay, so getting back to the question, for first order is A, or B, sorry. This is nonsense, that is nonsense. Okay. Alright, number 20. In a single propane molecule, there are how many sigma and how many pi bonds? Alright, so propane. Okay, 3 carbons, 8 hydrogens, and all the hydrogens want to be single bonded. Do all the carbons have at least 4 bonds? Yeah. Alright, again, sigma bonds are single bonds, so this only has sigma bonds, so the pi is 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 sigma. E. Alright. I know we're getting real close to the AP exam. I don't want you freaking out or getting super psyched out. You guys are, if you've been doing all these videos, you're really doing a nice job on preparing yourself. As always, I hope this video has helped.